All right. Hello and welcome to today's ACM Learning webinar. This webcast is part of ACM's commitment to lifelong learning and serving the over 100,000 computing professionals and students who are ACM members. It's very exciting to be here today. This is our biggest event this year. We had over 4,500 people register for this webinar. And it's my privilege to be your moderator today. My name is Michael Zeller. I am the CEO of Zementis, a software company focused on the operational deployment of predictive analytics. I also serve as the Secretary-Treasurer on the Executive Committee of ACM SIG-KDD. That is ACM's special interest group of knowledge discovery and data mining, and it is the premier international organization for data mining researchers and practitioners from academia, industry, and government. You can find my full bio on your screen in the webinar console. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. Our members can stay competitive in a constantly changing world of computing with a range of ACM learning centers at learning.acm.org. You can see some of the highlights on your screen. ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment. ACM provides a timely computing information published by ACM, including communications of the ACM and Q magazines. It provides access to the ACM Digital Library, which is the world's most comprehensive database of computing literature. It also provides many leading international conferences that draw experts on a broad spectrum of computing topics. And finally, it also supports education and research, including curriculum development, teacher training, and ACM Turing and ACM Infosys Foundation Awards. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. Before we get started today, I'd like to mention a few housekeeping items shown on the slide in front of you. In the top right corner of the slide area on your screen, there's a button that will allow you to enlarge the slides. You may also enlarge the slides at any time by dragging the corner of the slide window, and the slides will advance automatically throughout the event. During this presentation, you can minimize the slide area, QA, and bio screens using the buttons at the bottom panel. You can also use a number of widgets, also on the bottom panel, including Facebook, Twitter, Wikipedia, and a resource list where you can get a copy of the slides. Should you experience any problems with our web interface, then please press F5 in Windows, Command plus R if you're on a Mac, refresh your browser if you're on a mobile device, or close and relaunch your presentation. You can also visit the webcast help guide by clicking on the help widget. To control volume, please adjust the master volume on your computer. At the end of our presentation, we will have time for questions, and I'm assuming we'll have lots of questions. As I mentioned, this is our biggest event this year, and so if you think about any questions during the presentations, please type it into the Q&A box and click on the submit button. You don't need to wait until the end of the presentation to begin submitting questions. You may also use the Q&A box to suggest future webinar topics. At the end of the presentation, you'll see a short survey in your browser. Please take a minute to fill it out and help us improve our webinars. The session, finally, is being recorded and will be archived. You will receive an automatic email notification when it is available, or you can check learning.acm.org in a few days for updates. You can also use Facebook and Twitter, the widget at the bottom of your panel, to share the presentation link with your friends, as well as tweet comments and questions using the hashtag ACM Webinar Hadoop. We'll be watching for your tweets. And now, without further ado, today's presentation is Simplifying Big Data with Hadoop by Denny Lee. Allow me to introduce our speaker. Denny Lee is a senior director and startup entrepreneur who specializes in leading, architecting, implementing, and delivering solutions to solve complex data problems. As a passionate technologist, he has worked with numerous companies to solve their immense analytics problems, both on-premises and in the cloud. Notable examples of Denny's work include HDInsight for Windows Azure, which is Hadoop as a service for Microsoft's multi-tenant cloud, as well as Yahoo's 24 terabyte SQL Server Analysis Services. So, Denny, we look forward to your presentation here today. The stage is all yours.
Perfect. Well, thank you very much for those kind introductions, and let's jump right into it. So if there are no other questions, I'm going to jump right into the definitions of what is big data. Please note, just as Michael had called out, you can definitely ask questions during the presentation, and if there are any questions that are very succinct to the slide that you're seeing in front of you, we'll try to answer them during the session. We've got plenty of slides for you to look at. So jumping into what is big data, there's plenty of people that will go ahead and talk about how there's the 4 V's of big data. And in fact, I'm going to go to that in a second, but I'm going to start with just more straightforward wording, right? Big data, it's large. It's something that you typically you'll probably have more data than what's inside your iPhone, for sake of argument. It's also typically very complex. And what we mean by complex is that it isn't just comma delimited or tab delimited formats. You're typically dealing with data that have all sorts of different data types, different data formats. There can be binary, they can be JSON. But basically what it boils down to is that it's not a straightforward, I can take the information, put it into Excel or to Tableau or whatever else and make sense of it. And the other key thing is it's typically unstructured. Now, I actually don't like using that word unstructured. I actually prefer to use the word semi-structured, but a lot of people use that word, so that's why I'm choosing to use that word in the slide. Now, the reason I'm using that word is because I prefer semi-structured is because even if it's free text, let's use the example of medical notes, right? A doctor's medical notes for a patient. We typically call that unstructured data, but it really is semi-structured. It's just hard to make sense of what the structure is. Now, presuming you can make sense of the doctor's notes at all in terms of the handwriting, there actually is a structure of some type, as in this is the diagnostic code, this is how the person was, how they're feeling, and what we're trying to do to help the patient, right? So there actually is some form of structure, and for that matter, if we're going into the semantic debate, there is structure because it's actually, well, words. And so there is structure within the English or whatever language you're using. So that's why I typically like using the word semi-structured versus unstructured. So I apologize for rattling into that particular topic. But the idea is that it's not like it's a nice hierarchical format. Why it's actually there's a nice hierarchy, a nice structure to this information. It's actually harder to make sense of it. Now, Shanda, there was a quick question that was, as in, why is big data so important? And the answer, actually, I'm going to get into that in a few slides. But the gist of why big data is so important is because in the last 2 years, we've pretty much created 90% of the world's data. And as we progress, there is so much machine-generated data, whether it's from your smartphone mobile devices, whether it's from the iBeacons that are going to be in airports, the smart refrigerators, right? There's a lot of information that's being sent back and forth that's going that you want to track, record, and process and make sense of. And so since a lot of this is now automated or machine-generated data as opposed to human-generated data, to make sense of it, that's why there's this nice overbloated buzzword called big data to try to help make sense of all of this information. Okay, and so that's the reason why big data is so important. Okay, so now that I've talked about it in the context of straightforward words, let's go into a Gartner definition of big data, which is the 4 V's of big data, which is volume, velocity, variability, and variety. And basically what can be handled here is that volume, basically we're trying to say, as you look at the x-axis as you're going up on the right side, is that traditional BI systems can actually handle volume, right, up to a point. The example that Michael had called out during my introduction was that, for example, I had helped the folks at Yahoo build the largest analysis services cube on the planet, and that was 24 terabytes. The source of that cube is 2 petabytes in a 14 petabyte cluster. All right, so we can get BI systems to handle a massive amount of volume, right? But what it boils down to is that at some point you actually exceed the physical limits of vertical scalability. That's the nice fancy way of saying it. What that really means is that a single box, I can't go beyond the physical boundaries of what a physical box can actually handle for me. So for example, that's why Yahoo has a very large Hadoop cluster, and for that matter, the creators of Hadoop, because they need to spread this data across multiple servers, not just on a single server by itself. And so that's what we mean by volume in this case. Velocity means the decision window is small compared to the data change rate. And what this basically translates to is that if I was to form a question and ask you, hey, how long does it take to create a data warehouse? A lot of you would respond somewhere between 6 to 9 months, if at all, because it takes forever to do the speccing and then to do the prototyping and then trying to get the data into your database and then build the appropriate partitions and indexes and so forth and so forth and so forth. Lots of fun, right? Please denote sarcasm in my voice on that one. But the context is that, but I don't know even if I want this data, right? That's a key tenet of big data, or the velocity of big data, is that, well, I want to store it, but I don't have time to figure out if I need it yet. I'll go later to figure out if I need it. And then, as opposed to placing all this data into a nice structured store, whether it's an Oracle or SQL Server or anything like that, or MySQL or Postgres, right? What I want to do is just simply hit the file system real fast, run a query, get the answer back. And so in order to make sense of the data within the context of the data warehouse, 6 to 9 months. Within the context of a Hadoop query against a bunch of files that you saved, yes, maybe the query takes a while. Maybe it takes 2 hours, 2 days to run, but that's still significantly faster than the 6 to 9 months to build a data warehouse. And that's the key call out of velocity, that you can figure out what data you need if you need to even keep it, and if you do, at least you can store it in a somewhat safe manner, and if you don't need it, you can delete it right away. That's what we talk about velocity. In the case of variety, what we mean is that there are a lot of different formats of data. Right now, today, if you're asking me the question, like what are the popular varieties we're dealing with, I would say things like JSON, traditional CSV/tab delimited files. I would also say things like Parquet, ORC file, also protobufs, and potentially Avro as well. But that's my answer for today. And where it gets funky really fast, actually, is that you ask me that same question tomorrow or 6 months from now, there's going to be a whole new set of data types, data formats that are going to come into play. And so that makes integrating or merging the different sets of data together really, really difficult. And so the idea of a Hadoop cluster, again, when it comes to big data, is that I actually have the capability, I have some tools that give me the capability to integrate or merge together all of these different data formats so I can make sense of the stuff in one place, as opposed to needing to have multiple disparate tools to make sense of this information. And the final point in terms of variability, well, that's basically saying that because all the data is machine generated, what's happening here is that it's really hard to make sense of the information on its own. What you typically need to do is actually merge together multiple sources of data or multiple variables and actually piece together that together to actually make sense of what's going on. I mean, a crude example is like a key value pair that says A equals 1 is red. Well, that's great. At 1 o'clock, A equals 1 is red, but at 2 o'clock, A equals 1 is blue. Right. So the confoundance of variability is basically saying that, you know, I have a combination of both the key value pair and the time to actually understand what it actually means. Right. So put this all together in terms of these 4 different definitions, you know, volume, velocity, variety, variability. The key thing about big data is that it's not one of these problems that actually is going to be problematic. In other words, if it's just volume by itself, I can probably build a distributed data warehouse. If it's variety, I can probably write some really fast Python code to solve it. If it's velocity, I can probably build a CP, just event processing tool, or some of my own custom code to do that, and so forth and so forth. What makes big data really funky is that I actually have to handle all of them. Okay, in other words, I have the volume problem and the variety problem and the velocity problem and the variability problem. And because I have to solve 2, 3, or all 4 out of 4 of these V's, that's what makes it a big data problem, and that's why traditional methodologies to solve this problem isn't necessarily going to be the way to do it. It doesn't, I mean, by the way, I do want to be very clear. It doesn't mean traditional relational systems can't actually solve it. I'm just saying that, but that's the reason why you start looking in the realm of big data, because all of a sudden you actually have multiple, 4 of these V's to actually go tackle, okay? Okay, so I'm going to switch gears a little bit, and I'm going to go ahead and talking about scale up versus scale out. And why is that important? The reason you care from, even for a business person who's actually on the line as opposed to necessarily an engineer, right? Why would you care about scale up versus scale out? The reason is because scaling up is, we're talking about, we're going to be limiting ourselves to one machine, but we're going to max out what that one machine is capable of doing, right? So this is a great example of that, and I like using space analogies, is like the Hubble telescope, right? With the Hubble telescope, it's one uber scale-up system. It's an awesomely large telescope. It requires extremely specialized equipment. Last time I checked, what NASA builds typically is not what we call commodity hardware, so it's very non-commodity hardware to work with. Right, and so basically you can get some awesome pictures, and this in this case is actually a picture of the antenna galaxies, which is about 45 million light years away. And by the way, if you want more pictures like this, I just suggest you go to hubblesite.org. They actually have lots of cool images from the Hubble telescope. But the main issue with it is a single point of failure, which sort of bites, right? When the telescope went up originally, they had a problem with the lens, and so they actually had to go through multiple times to get to go into space to go fix it. Now, fortunately, fixing our database or our hardware isn't as difficult as being an astronaut to go in a space shuttle to do such a thing. But nevertheless, the context is that it's a single point failure. If and when it fails, it becomes really, really difficult to fix it. Okay. Now, this is the example of scaling up. Now, also, as a quick thing to note, it's not like scale up isn't actually a good idea. We actually have some really awesome pictures from it, but that there are the detriments or the issues that go with scale up, and as noted, specialized equipment, single point of failure. Okay, now I'm going to switch gears a little bit. All right, so in this case, I'm going to talk about scale out or commoditized distribution. Okay, this is yet another picture in this case, of the giant galactic nebula from a Hubble site, except if I want to go ahead and track radio waves, okay, and so radio waves basically, by the way, is because, why are we tracking radio waves? Is because basically we're trying to do a project called SETI, or S-E-T-I, and then for those who are really sci-fi folks here, SETI stands for the Search for Extraterrestrial Intelligence. So yes, ladies and gentlemen, we are searching for aliens, okay? So why are we searching for aliens? Because basically, if you have artificial radio waves being generated, that is a sign of intelligence, because it takes intelligence to create radio waves. That's what it boils down to. So now we're searching for radio waves. Okay, so that sounds pretty cool, all right, at least for any sci-fi geek. So we have, in order for us to do that, we have these radio observatories placed all over the planet to go ahead and actually try to track these radio waves. And then we shove a lot of this data into supercomputers. In this case, this is a picture of the Barcelona Supercomputer Center, right, where a lot of this stuff goes into. But how do we actually make sense of a lot of this data? What's interesting about the concept is actually there's a project called SETI at Home, which basically is just a screensaver that you install on your computer. And what happens is basically information is sent from the SETI projects to your computer, about 20 megabytes. So when your screensaver kicks on at night, it'll go ahead and process that data and then send it back, okay? Basically, it is your screensaver on your home computer that's currently trying to make sense of if there are, in fact, extraterrestrial intelligence out there, which is pretty sweet. Now, in this case, SETI at Home has 5.2 million participants. So at any one point in time, there are hundreds, tens of thousands to hundreds of thousands, potentially even millions of computers at any one point in time that's actually processing all of that data. So very much the key example of distributed computing, big time commoditized distribution, because it's just using the screensaver on your home computer, right? So it's analogous to the idea of commoditized distributed computing, where you distribute the problem and calculate it locally. You're engaged with hundreds of thousands of machines, and while there are many points of failures, you basically design a system to auto-replicate to prevent that from being a problem, okay? And so the context basically is that when you look at the data world, in the traditional data world sense, databases in this case, right, they are the scale-up, typically scale-up design. I'm not going to include things like PDW or Teradata or Oracle RAC or things like that, but I'm just talking about the traditional database or data warehousing sense, okay, like in which they're all about scaling up a single machine, okay? And when you look at the scale-out design, this is where analogous to Hadoop, this little yellow elephant, which represents Hadoop. I'll go into that in a second. But the idea is that now I solve the new hard problem, which is how do I distribute and replicate all of my data across multiple servers, and then also in return query all of this data that has now been distributed across multiple servers, okay? And so that's what basically the key tenets of scaling out. And as we've progressed and as we built better and better technology, the heart of the big data world is basically the realization that the distribution and so forth, and the replication that goes with it is actually the real hard problem, because at some point you have more data than a single machine will ever be able to help you solve. And since you have that particular problem, then what we need to do is actually, well, push that data across multiple servers and replicate it so that way we won't lose the data, and then be able to have a mechanism to query all of this data, okay? So that's the key tenet of the key concept for scale out. Okay, so now we're going to jump over to Hadoop. Why? What is this Hadoop stuff? Why is it important, and why do we care? There are other big data type technologies that are out there, but why Hadoop, okay? Well, it's synonymous with the big data movement. Okay, that's the key thing, right? Like I've been sort of harping on the last couple of slides, is the infrastructure to automatically distribute and replicate data across multiple nodes, okay? It's inspired by Google's MapReduce and GFS papers, and basically the key components as per this graph, okay, this is yellow elephant, there's two real layers to Hadoop. There's a MapReduce layer, and there's an HDFS layer, okay? So the HDFS layer, which is a little bit easier to explain, is the Hadoop distributed file system. And the point of this file system is to go ahead and say, I will be able to push data into it, and it will auto-replicate and auto-push all of this data into multiple locations. So that's what the whole premise of Hadoop really is, okay? The whole premise of HDFS. In the case of MapReduce, basically it's about going ahead and saying, I'm going to run a map job and a reduce job. I'll go into that actually in a couple slides. But the idea here is that I will track each one of these map tasks or each one of these reduce tasks by building an infrastructure called a job tracker and also a task tracker. For every single query or process that I'm running, a job is generated. That job then generates multiple tasks that are then sent to every one of the nodes that are in your cluster. So that way, the task tracker now keeps track of that particular query that's being executed, and that's basically what the MapReduce layer does. Okay. All right. So let's see, here we go. Right. And small, funny little note here is that why is the Hadoop is being associated with this nice little yellow elephant is because it's actually based off of the Yahoo Nuts project back in 2003, which became Hadoop in 2005. That was actually named after the creator of Hadoop, Doug Cutting. His son's toy elephant was called Hadoop, and hence now that's why we have a big data infrastructure called Hadoop. Okay.
Hey, Danny, there's one question. Maybe we can take a quick question here in the middle.
Sure, of course.
Okay. So one of the questions is really relating between scaling up and scaling out. And so the one question is the only constraint, the only limitation of scaling up on a single machine that it is a single point of failure, or are there other limitations?
Well, absolutely, the single point of failure is absolutely a very important concept, but it's not the only worry in terms of about scale in terms of scaling up. The other key thing is that we actually at some point, because we're pushing so much data across the wire, it becomes actually a little bit difficult for us to handle. We're starting to hit the boundaries of physics about how fast and how much of data we can push from disks into the CPU, into memory to do the calculation. And that's part of the reason why scaling out is actually important, because we want to be able to distribute that query to multiple servers, so that way we can basically partition the problem down or shard the problem down, depending on how people want to phrase it. Just as a quick note, I think we'll still have enough time for this, but later on the slides, I actually get into a little bit more about the scaling up versus scaling out in terms of the single point of failure as well. There's actually a couple animations in terms of why the scaling out is actually really cool when it comes to big data. I hope that helps that.
Yeah. Perfect. Thank you.
Okay, perfect. Okay, so I'm going to jump right into sorry, I'm actually there we go. What I want to do is just a quick example of comparing databases and MapReduce. And so here's a quick call out. This reference is from Tom White's Hadoop, the Definitive Guide. There was an ask earlier. There was an ask earlier in one of the Q&As about which is a very good book or my personal recommendation for a resource for Hadoop. It absolutely is Tom White's Hadoop, the Definitive Guide. So if you're interested in learning, I would absolutely start off with that book, okay? But the key call-outs as per the slide is that when you look at traditional database systems, we're talking about gigabytes or terabytes, versus in the case of MapReduce, we're talking about petabytes to hexabytes, right? The access patterns of database systems are interactive and batch, but at least for MapReduce v1, the current version, it's batch. Now, there's also a MapReduce version 2, or what they also call Yarn. Those actually allow for much more interactive access against that data, but that's going outside the bounds of this particular slide deck right now. So I'll skip that for now, but I did want to call that out. The way databases are designed, they are designed very well for read, write many times, but in the case of MapReduce, very much write once and read many times. But in return, MapReduce allows you for a very dynamic schema versus a static schema in databases. And the integrity is actually, for traditional database systems, it's very high, right? It's called ACID compliance. And so what you're really trying to do is you're trying to make sure that if you say that transaction exists, then you're good to go. That transaction actually occurred. Versus in the MapReduce world, that's not so much, right? It's basically, base stands for basically available, steady state, eventually consistent. And that's a key phrase here, eventually consistent. So the data may not actually be consistent when you push it into your Hadoop cluster. It'll eventually happen, but maybe not right now. So that's the quick call out, okay? And so from a tech perspective, that's actually how you want to really look at the comparison between the two, okay? Okay, let's see. So let's jump into a quick example now, okay? And so what we have here is I'm going to just show you, actually I'll just jump right into what a Java MapReduce word count function looks like. So apologies to all of the folks here on the line that are not necessarily engineers or geeks, but the idea is that the simplicity of MapReduce is that basically you have a map function, which basically says, okay, if I'm doing a word count, in other words, I'm counting the number of words inside a text file, right? Basically, all I'm going to do is I'm going to tokenize the text that I'm reading that basically says, okay, if it's a space, if it's a tab, if it's a character return, go ahead, that's a break. That's not an actual token, but then each word that I receive, that'll be a token. So in other words, in essence, from the standpoint of what this is, I'm taking each word and I'm shoving it into an array, okay? So that's what really the map part of this is, and the reduce portion of this is actually to simply say, okay, cool, now go ahead and give me a count on all this, or a summation of the number of these words, okay? So that's really all MapReduce is, okay? So what's interesting about it is that, is that when you look at how you want to do a query with against like text like this, in a traditional relational database system, it's going to be pretty hard to do such a thing. But in the case of Hadoop, it's very well designed. So, for example, in this particular example that you're seeing on the screen, which is the Project Gutenberg ebook of the notebooks of Leonardo da Vinci, it's able to quickly, well, I won't say quickly, I'm sorry. It's able to count, the number of times it sees the word law, the number of times it sees the word project, and so forth and so forth. And so that's a simple example of what MapReduce is. And that was actually the key case of why Hadoop was built. It was actually to basically figure out what were the keywords that people were searching for, in this case, the Yahoo search engine. What are the keywords people are using, right? But what happened, and that what made things super interesting, was that it became possible to start doing much more complicated, well, what was originally thought of complicated analytics, okay? So, for example, I'm now going to show you a weblog. So this is obviously a very fake weblog, because if anybody has an eagle eye, you'll notice that there shouldn't be a 588 IPv4 address, okay, inside a log. So very fake, but I want to extract the information, in this case the GUID, the key value pair of I sub CY and lang, because I want to actually extract the country and extract the language, okay? So in this case, if I was to go with the traditional relational database model, sure, I could do comma delimited and extract out GUID and whatever else and the parameters. But I still have to make sense of those gobbledygook of parameters, the ISOCY and language, okay? So a little tricky, but what happens is that in the case of the Hadoop infrastructure, there is a language called Hive. Hive is a data warehousing framework that you put on top of, that actually makes use of MapReduce, makes use of the Hadoop infrastructure. And then I can write a query like this, which is select. It looks very much like SQL, select GUID, string to map, parameter, ISOCY and language, and from this weblog, and then basically the results will be the GUID, the ISOCY, which is in this case BR, which represents Brazil, and the language 1046, which represents Portuguese in Brazil. Okay, so now I have the query to come back very easily, and so this little really cool thing is that now I'm actually able to make sense of what was semi-structured data that was stored inside a weblog, and yet I can use a SQL-like query language to make sense of this information. And so this is where the power of Hadoop started coming in, that we could, because Facebook created Hive and Yahoo created Pig, and the flexibility of MapReduce in general, we were starting to able to do far more complicated things than the original word count that we were trying to do, okay? And so that's what's really sort of cool about all this, okay? The other quick call out is that, actually, you know what? I'm going to skip that for now, but basically the context is that you have the flexibility to be able to go ahead and make sense of this data, and that's what's really cool about all this, okay? And so there is a link here for a MapReduce tutorial. I'm not going to get into it too deeply because I figured that'll be, or unless you want to do it during the Q&A portion of it. But the quick call out that I want to say is that while we keep on saying MapReduce, the reality is that it's actually not just MapReduce. It's splitting, mapping, shuffling, reducing in order to actually get the value. There's a link inside the slide to a great online course from Stanford, a tutorial about how MapReduce works. So if you're interested in diving into those details, I highly recommend this tutorial for you to go ahead and look at it, okay? All right. The reason I wanted to go ahead and skip this part is because I did want to call out, as per one of the original questions about single point of failure, okay? It's about where, when you look at database systems, it's about moving data to the compute, while in the case of these Hadoop systems, it's about, or big data systems, it's about moving compute to the data. And here's what I mean by this, okay? So when you look at this particular graphic, what you actually have here is two servers, okay, two database servers. Those blue widgets, okay, or platters are basically to represent disks, okay? The blue arrows are to represent fiber channel connections, basically from your disk array to your server. So in other words, on the left side is two servers. On the right side, you have something like a SAN that basically holds a bunch of your data. Okay, and so the connection between the SAN and the server by those blue arrow, which is the fiber channel connection, that's what the blue arrow stands for. Okay, and the green represents the Ethernet connections. Okay. So what's really cool about this is that, you know, because of this type of infrastructure, I'm able to put data, get the data from my disk in the SAN, push it into my database server extremely quickly, and make sense of the data extremely quickly, which is awesome, right? You know, so that's what's great about these scale-up systems, that I can run a query against a few billion rows of data, and frankly, I'm going to get that back, that query back in hundreds of milliseconds, which is sweet. Okay. But the problem that you're going to run into is that if there's a failure at any one point of these places, for example, if the disks were to fail, okay, or if the fiber channel connections from the disks to your server fails, or if you go ahead and lose Ethernet connection, then what ends up happening here is that you get, you basically lose the database altogether, okay? Well, okay, sorry, that's a little too harsh, but you lose the ability to query the database and get information back from the database until you fix something. You've fixed the disks, you've fixed the fiber channel connections, you've fixed the Ethernet connections, okay? And this becomes more and more complicated when you have more and more servers, because you become much more dependent on these complicated systems to hold disks. Anybody who has actually ever maintained a SAN can vouch for me on this one. Can correct fiber channel connections, correct Ethernet connections, so it can be very problematic. Now, it's not to say that this is a bad idea. It's actually been a great idea for quite a while, because it's all about this ACID concept, atomicity, consistency, isolation, durability. We basically want to make sure that if we say a transaction occurred, and it occurred when we said it did, okay? We know the value of the data. We can get the query back extremely quickly when you work within the bounds of physics to actually ask that question. But the problem with it is that the distribution of this problem becomes really hard to do, and that if there's any one of these failures, it actually can make it near impossible to query the data. And that's a very important thing to call out. Okay? Now, in the scale-out side of things, okay? This is where the Hadoop or the NoSQL, what they're talking about is moving compute to the data, okay? And so the key important concept here is that if I have a failure, I should rephrase. The screen that you're looking at, you've got 6 servers. I put the database icon there. That's not technically the best way of looking at it, but you've got a bunch of disks in each one of these servers. You've got Ethernet connections between all of them. So what happens is that when I have a file, which is here on the right side, it automatically gets pushed into and replicated into multiple locations on this cluster. So now it's in this one particular file, for sake of argument, is now in 3 different locations. So what happens is that if I actually were to lose a bunch of Ethernet connections or lose a bunch of disks, I'm actually still okay because the data is still there. I have the other 3 servers to go ahead and query for this information, which is pretty nice, okay? And so that's the idea behind Hadoop, which is, and the heart of these big data systems, that we distribute and replicate the data. We have a mechanism to do that such that even if I was to lose some of my hardware, there are still other paths to get to the data that I have and to get the answer that I need. And that's a pretty important concept, because as you have more and more data to work with, it becomes harder and harder and harder to keep that data just in one server. So if you're going to now push it across to multiple servers, multiple nodes, you have to make sure that you have a mechanism to be able to distribute, to replicate, to ensure that you keep the safety of this data, and to be able to query against all the different the distributions of that data. Okay, and so that's a key, quick, important call out. So I realize that we're actually at 40 past the hour. I'm actually going to go ahead and just talk for about 5 more minutes, on some of the more high-level concepts. So I'm going to skip some slides just a little bit, just to frame the rest of this conversation. And then once we're done, we'll switch right to the Q&A. I hope that's okay. Okay, so just to finish it up, why is Hadoop and big data systems or the NoSQL world so important? The reason it's so important is because there's a heck of a lot of business value. Now, some of the numbers that you see here seem a little blown out of proportion, but it's actually based off of the McKinsey Global Institute report called Big Data, the Next Frontier. Okay. Now, the numbers, even to myself, seem a little big, like, in other words, $300 billion potential annual value to the U.S. healthcare, or 1.5 million more data-savvy managers in the U.S. alone. But nevertheless, irrelevant of what the numbers are, there's actually a huge amount of business value. And so from a technical perspective, of what I did is I included this particular tidbit about how Facebook moved 30 petabytes of Hadoop data. They actually were able to migrate the data from one set of clusters to another set of clusters, where basically they were able to do it efficiently and much ironically easier than your traditional warehouse systems that were using SAN and NAS. Okay, so they're actually able to keep. They were able to show how they were efficiently able to keep an active multi-petabyte cluster properly replicated with only a small amount of lag. And that, from a keeping the data safe, being able to query the data at any point in time, is actually super, super important. And that's really cool. And because of all of this, in terms of the business value, this is the one final thing that I wanted to add up is actually a cool quote from Kovas Baguda. Where basically this illustrates a new thesis of the collective wisdom emerging from the valley. If the technology is not your core value add, it should be open source, because then others can improve it and potential future employees can learn it. This rising tide lifts all the boats and is just getting started. And that quick call out, the quick thing that goes within the world of Hadoop, basically what it boils down to is that Hadoop as an open source technology, it's actually being used by so many people, whether it's your Twitter, your Facebook, or anybody else. It's super, super exciting. And so a lot of people are all working together to enhance the technology, to make it better. And so, for example, you're looking at the cool things that are coming out now, such as MapReduce V2 and Yarn. You can look at, there's some questions about Impala and Hive. You look at Spark, which I'm a huge fan of. All of these different technologies are being created by others, and this is basically, Hadoop is pretty much the fundamental core tech that we have all built on top, sorry, not so much built on top of, but made use of or has excited the entire big data world. And so because it's all open source, we're actually able to share not just the technology itself, but also how we can better use it and how we can be more efficiently able to make sense of the data. Because at the end of everything I said, okay, what the key cool thing about the big data movement is that it's not about the technology anymore that makes this all important. It's the data that we have that actually becomes extremely valuable to everybody. So while I've been busily talking about the tech this entire time, it's our ability to make sense of the data, it's our ability to query the data, it's our ability to find new models within the data that makes it all super exciting. Okay? All right, so I think that's it for the speaking portion of the session. As you can note, there are plenty of other slides. These slides will be available for you to download. But meanwhile, let's go right to the Q&A portion of this so we can have a little bit of fun on the question and answer period.
Okay, great. Thank you, Danny. This was very informative. We have lots and lots of questions, and I'm trying to kind of group them a little bit. So since we were just talking about kind of the database topics quite a bit, one of the question was, what kind of a database system or what kind of a database solution would you suggest on top of Hadoop? And maybe you can take this question to kind of contrast a little bit the different flavors. So from HBase to Hive, there's a question about Impala. So there's a whole zoo of different options, and maybe you can spend a few minutes on the database options on top of Hadoop, Danny.
Sure, no problem at all. So let's start talking about databases by themselves, okay? So one of the key factoids about databases is that now we have more JDBC connections or Hive ODBC connections and or scoop drivers. You actually have a much bigger variety of connection points from traditional database systems into Hadoop. So often people term Hadoop as like the big digital sandbox or phrases like that. So I'm going to jump away from the buzz a minute and just sort of get to the heart of the matter, which is that when you have lots of data, at some point you're going to want to get value out of it. And when you do get value out of it, you're going to go ahead and say to yourself, hey, cool, now I've actually, whether you meant it or not, you've structured the data because I needed these attributes or I needed these rows. I needed to filter by something, a where clause. I needed to go ahead and create out particular attributes or particular columns of data. So at some point, I want that answer to come back extremely quickly. Now, your options in the traditional database sense is then basically say, hey, let me just go ahead and now push the data out from my Hadoop cluster in this structured format, and now I can just prop it right into SQL Server or into MySQL or Postgres or Oracle. And so my response when it comes to the traditional database systems on which one would you prefer, my attitude is whatever you already know, okay? The ability to get this data from Hadoop into a relational database system is not the most efficient for any of them, but it's also not horrible for any of them, okay? It's basically the same idea. What ultimately is going to happen is that you basically, in its most base or raw form, is that basically you're bulk exporting data out of your Hadoop cluster, okay, and you're bulk inserting that same data delimited format into your database. And so if you happen to have strength in MySQL, go with that. Strength in Postgres, go with that, and so forth and so forth. So that's basically the idea of which database that you're talking about, okay? Now, in the case of the newer technologies, whether you're talking about an HBase or Cassandra or Impala or Spark or whatever else, the key aspect here is that they pretty much all work with Hadoop in one form or another. Even if they don't work with Hadoop in the traditional sense, they'll actually, they're either connectors or they're easy ways to go ahead and connect to HDFS, okay? Hadoop Distributed File System to get data from Hadoop into any of these other systems. And the answer for that is much more complicated and much more subtle because the real answer is what are you trying to actually do with the data? For example, HBase, it's made famous because of the Facebook. When you look at Facebook statuses and Facebook messages, that's HBase, right? That's how you get that type of high volatility, only looking at current snapshot data, so perfect. That's what HBase is perfect for. Well, if that's your scenario, then by all means, build your system to get the data from Hadoop, to HBase. Cassandra is a great story. In addition to the really cool Netflix, where they basically replaced Oracle with Cassandra, and there's also a really cool presentation by Evan Chan about interactive OLAP queries on top of Spark and Cassandra. Basically, if you're trying to go ahead and go with, when your focus is to go ahead and actually have to use something like a CQL, where you replicate the data so that way you can ensure that there's right consistency, then perfect. Cassandra is the perfect story for that. You have a way to get the data from Hadoop and Cassandra, and do your thing. The same is for Spark. The same is for all these other systems. It really depends on what you're trying to do. There's the real issue that we have in this new world of big data is that all these tech, it's very fragmented, and they're fragmented for the reason that everybody had built these technologies for their special purpose problems and then have adapted or made it a little bit more generic over time. But there's a root reason why MongoDB was created. There's a root reason why CouchDB was created that weren't entirely the same, and hence why they created these technologies. And getting the data from Hadoop into these tech, almost all of them have figured out ways to efficiently do that. Or at least not poorly do that, okay? And they're all roughly about the same. Mm-hmm. So the question for you really is about how and what you're trying to do.
Excellent. Well, thanks, Danny. Yeah, these were a lot of technical, detailed questions as well along the way, which are going to be difficult to answer in a very large audience like this. But there's one particular question that was, I thought, coming all the way to the beginning, almost to your slide sets. It asked about the connection between data mining and big data, and maybe you can talk a little bit about big data and data mining opportunities.
Sure, no problem at all. So data mining and machine learning and basically and all of their different variants is super exciting. Why? Because now we finally start doing statistics and actual modeling. The buzzword of the day is data scientists, right? But statistics and data modeling back against our data, that's a heck of a lot more complicated than just counts, aggregates, and trends. Now, what data scientists have done traditionally is basically they go to a database, they export the data, and then they run their models. And most of these technologies are very good at scale up. Basically, you use up all the memory in that box to create that model. Once the model is created, then you can go ahead and then run queries based off of that model. You put some input data into it, hit the model, output result. Yay, I have what I want, right? In the case of big data, what it gives the ability for data scientists, provided it's a technology that actually can be distributed across the clusters, is that now you can solve your data mining or machine learning problems in a distributed fashion, not on a single server. And while you as a individual may not care about this so much, what happens is that if you're collecting lots and lots and lots of data, for example, if you look at my company, which is Concur, we're travel and expense. So it's not that interesting all by itself because we got travel data and we got expense data. Except the cool thing about this is that we have a pretty good idea of what type of stuff, where you're about to go. And for example, you need to take a flight from San Francisco to Seattle. Guess what? That's part of our travel tool. Cool. But yet, I want to merge all that data with all the weather data that we have, right? So there's a whole bunch of weather data that's in very complicated formats or JSON formats or whatever else that I'm bringing in. There's also FAA alerts, and there's also delay traffic alerts. So I want to merge all that data together. So now it's all sitting in my Hadoop cluster because it's taken a heck of a lot of space for me to save all the stuff. So as opposed to now to create a model that can predict whether whether my flight's going to get canceled or not, instead of trying to move all of that data out of my cluster into one box, because we have tools like Spark or tools like Hadoop or Ripe, I'm now able to go ahead and calculate the models against the data directly on the distributed cluster. So I'm actually able to do some really cool things. And that's the promise of data mining and big data working together. Hope that answers that question.
Perfect. Thank you, Danny. Yeah, I think this was a very deep, good explanation. I think what we've seen here also is that big data drives a lot of the interest in data mining. I sometimes call it the V number 5, the value, right? It's perfect. It's a perfect application for statistical algorithms, machine learning, and predictive analytics. So this is, I think, a very good time to merge the two, and we've seen that happen in industry as well as in research. Another question, I think, going back to almost the very beginning, there was a lot of questions about unstructured data, unstructured versus structured versus semi-structured. I think people were a little confused. Maybe can kind of give a few examples of the different data types. One question was specifically on what's big data in medical field, for example, and then also relate that to complexity. So does unstructured mean more complex, or is there no relationship?
Okay, yeah, so this is a pretty loaded question, so let me try to break this into two different parts. Let's start with what I mean by unstructured versus semi-structured. And so I'm a bit of a geek when it comes to, or on the semantical difference between the word unstructured versus semi-structured. And so a lot of us in the big data world, we use the term unstructured, which is, but the problem is from a semantic statement, right? Unstructured means there's no structure at all. So in other words, it's a bag of letters or a bag of characters, right? As opposed to a bag of words, okay? In other words, because if you've got actual words like the, patient, doctor, right? Those are words. There's still some structure to it. There's a grammatical structure, there's a structure to create the words, and so that's why I don't like using the word, the terminology unstructured. I'd rather use the term semi-structured because there still is meaning in the stuff. It might be hard to extract the meaning, but there actually is meaning in this information. There is some context inside that information. So that's why I like using the terminology semi-structured versus unstructured. And so apologies for being a little bit too much of an obsessive compulsive on that particular terminology thing, but that's basically what it boils down to, okay? Now, switching to the second part of that question, when you're saying examples of semi-structured, well, yeah, I mean, even if it's like using the medical space, we're talking about doctors or doctors' patient notes, right, that are typed in or recorded and then typed into the patient record, the electronic patient record, right? That is text that I want to extract out of. There is some semantic meaning or sentiment meaning or some other contextual meaning inside those patient notes that's telling me how well a patient is doing or what is his or her diagnosis or things like that that are outside the boundaries of just the ICD-9, the codes that indicate, or the prescription codes or the diagnosis codes, the various codes in the medical industry to describe what tests or what ailment is happening to the patient. In the traditional sense of structured world, the ICD-9 code, the procedure code, the diagnosis code, these are structured things because I've already made it very clear, here is what the ailment is, here's what my diagnosis is, and so forth. So that's very structured. The things like your patient notes, doctor-patient notes, some of the nonsensical notes related to lab results, these are where it becomes more semi-structured because now I actually have to do some interesting parsing to get the meaning out of the data. Okay? So that's an example of semi-structured in the patient world, okay, or the medical world. Semi-structured in the sense of what a lot of us are doing. For example, when you talk about social media or whatever else, things like JSON, right? Basically, there is a hierarchy implied within JSON and XML for how the attributes are organized, but then you have a hierarchy within inside that JSON that says things like, okay, here's your user profile, here's my Twitter handle, here's the status of the day, here's how many retweets that happened, here's the URL links, and here are the hashtags or keywords that are associated with my tweet, okay, using that as an example. That's information that's placed in JSON format. The reason we often use JSON format is because it allows us to actually add additional attributes as time progresses, because we realize there might be some interesting things like, for example, oh, now I want to add location services information into my tweet that I know where the person actually did the tweet, right? So originally there was no location, now there is, so we just add another attribute to the JSON that allows me to record that information. Okay, did I actually answer all the questions? Okay, cool.
I think so. Well, we have probably 1,000 more questions. Unfortunately, I'm afraid we ran out of time for today. So I'd like to thank Denny Lee again for his very informative presentation and the very insightful, interactive answers to many of the questions. Although we have plenty more to go, we could probably go another few hours. So special thanks to each one of you today for taking the time to attend and to participate. There will be a recording of this webinar available online in a few days at learning.acm.org/webinar. You can find more announcements on upcoming webinars and other ACM activities at the same location. And also, please fill out the quick survey where you can suggest future topics or speakers, which you should see on your screen very shortly. And thank you again. This was a very exciting webinar. This is your moderator, Michael Zeller, saying goodbye for now, and take care. Thanks again for joining us today.